Usually, when we talk about a medical diagnosis, there's this expectation of like absolute mechanical precision.
Right.
Like if you break your arm, the X-ray shows this jagged white line. The doctor points right at it and just says, "There it is."
Yeah, it's very binary.
Exactly. It's visible. It's comforting. It's either broken or it's not broken.
We definitely crave that kind of absolute categorization in medicine. We just want the test to hand us the answer.
But then you step into the world of immunohematology.
Okay.
You step into the blood bank at like 2 in the morning and suddenly that comforting X-ray machine is just gone.
Completely gone.
We're looking at a diagnostic landscape that is incredibly murky. I mean, you are staring at a rack of glass test tubes, and a tiny wisp of red cells at the bottom of a cylinder is the only thing standing between your patient and a potentially fatal transfusion reaction.
It really is the absolute definition of diagnostic muddy waters. The reactions we interpret in those tubes, they're influenced by temperature, by pH, by ionic strength, and, well, really by the bizarre evolutionary history of the human immune system.
Which is exactly why we're here today. So if you're listening to this, you are likely in the trenches preparing for the ASCP MLS board exam.
Or you're just a massive blood bank nerd, which is also great.
Hey, we love those too. But we've designed this specific deep dive as a highly focused, immersive study session tailored entirely for you.
Yeah, our mission here is to move completely beyond rote memorization.
Right, because memorizing charts is fine if you just want to pass a weekly quiz, but the board exam, they want to test your actual clinical understanding.
They want to know if you really understand the underlying physics and biology of that tiny wisp of red cells.
So I am going to be your enthusiastic study partner, just trying to make sense of the madness, and sitting across from me is your seasoned MLS veteran, ready to guide us through the underlying mechanics of these high-yield immunohematology topics.
I am thrilled to be diving into this material because honestly, when you understand the underlying mechanics of what is happening in those tubes, like the why and the how, you really don't need to rely on flashcards anymore.
That's the dream.
It is. The answers simply present themselves as logical conclusions.
Okay, so before we can even begin to identify what's going wrong in a blood bank tube, we have to start at the very bottom.
We have to understand how these blood types are built from the ground up.
Right, because if you look at a standard biology textbook, they usually just show a red blood cell with little like solid spikes sticking out of it, and those spikes are labeled A or B.
Yeah, but an antigen isn't a solid plastic spike, is it?
Not at all.
No. When we look at the genetic pathway in the antigens of the ABO system, we're actually looking at complex chains of sugar molecules extending out from the lipid bilayer of the cell membrane.
Okay.
And the specificity of the antigen, the thing that makes it an A antigen versus a B antigen, is determined entirely by a single specific sugar molecule sitting at the very end of that chain.
And we call this terminal sugar the immunodominant sugar, right?
Exactly. The immunodominant sugar.
So walk us through this biological assembly line. Like, how do we get from a blank, newly minted red blood cell to a fully realized group A or group B cell?
Well, everything begins with something called a precursor substance. Visualize this as just a bare, inactive chain of carbohydrates extending off the red blood cell membrane.
So it's just sitting there waiting for instructions.
Yeah, exactly. The very first critical step in this assembly line relies on the inheritance of the H gene.
The H gene.
Right. If you inherit a functional H gene, that gene produces a specific enzyme, a glycosyltransferase.
Okay, and what does that enzyme do?
Its sole job is to pick up a specific sugar called fucose and attach it to that bare precursor substance.
So once that fucose is attached, the precursor substance gets like an operational upgrade.
Precisely. It's no longer just a bare chain. It is now officially classified as the H substance.
Okay, and that H substance is the fundamental prerequisite for everything else that follows in the ABO system, right?
It really is. It's the molecular landing pad.
The landing pad, I like that.
Yeah, because only after you have successfully built that H substance can the A or B genes actually do their jobs.
So if you inherit the A gene, what happens?
It produces a different enzyme that comes along and adds its own specific immunodominant sugar onto the H substance landing pad.
And if you inherit the B gene...
It produces a different enzyme that adds a different sugar onto the H substance.
Okay, but what if you inherit the O gene? Because group O is the most common blood type in the world, so it must be doing something right.
Well, the O gene is fascinating because it's actually an amorph. It's a silent gene.
Wait, silent?
Yeah. It does not produce a functional enzyme at all. Because there's no functional enzyme, no U sugars are added to the chain.
So the cell just remains coated in that bare H substance.
Exactly.
I want to make sure I'm visualizing this correctly. And O patient's red cells are absolutely covered in H substance because nothing else ever got added on top to obscure it.
That's right. Because of that, Group O cells possess the absolute highest concentration of H antigen of any blood type.
Their landing pads are just completely exposed.
Yes.
Which brings us to a classic board exam trap, and really one of the most interesting genetic anomalies in the blood bank.
The Bombay phenotype.
Bombay phenotype. So what happens if a patient doesn't inherit that functional H gene in the first place?
Then you are describing the little h genotype. Because these individuals inherit two recessive H alleles, their bodies produce no fucose-transferring enzyme.
So fucose is never added to the precursor substance.
Therefore, they never create the H substance at all.
Let me try out an analogy here to see if this tracks for you.
Sure, go for it.
Think of the red blood cell as a bare plot of land. That bare plot is your precursor substance.
Okay.
The H substance is the concrete foundation you pour onto that land. The A and B genes are the paint colors for the house.
I see where you're going.
So, in the Bombay phenotype, you might theoretically inherit the buckets of paint like. Your DNA might contain the A or B genes, but without that concrete foundation, you cannot build the house.
Right.
The paint just washes away into the soil. There's physically nowhere for those A or B sugars to attach.
That is a highly accurate way to conceptualize the structural failure.
Awesome.
Because they lack that concrete foundation, their red cells have no H antigens, no A antigens, and no B antigens.
So imagine you're the technologist testing their blood in the lab. You drop standard anti-A and anti-B reagents into the tubes. What happens?
Nothing happens.
Nothing at all.
Right? There's nothing for the reagent antibodies to bind to, so there's zero agglutination. The tubes look completely clear.
And because they don't react with anti-A or anti-B, the technologist writes down that they forward type as a group O.
But they are not a true group O. And this is where the situation becomes clinically terrifying.
Yeah, let's get into that.
A true group O person has millions of copies of the H substance on their cells. A Bombay individual has zero. Because their immune system has never encountered the H antigen in their entire life, their body recognizes it as a highly dangerous foreign invader.
Oh, wow. So they just naturally produce anti-H.
They do. Bombay individuals naturally produce a very strong, clinically significant anti-H antibody in their plasma.
And since almost every single human being on Earth, including all those normal Group O donors sitting in the blood bank refrigerator, has H substance on their red cells.
Exactly.
Transfusing normal Group O blood into a Bombay patient would be catastrophic.
Their anti-H antibodies would immediately attack and destroy those Group O donor cells. It would initiate a massive, potentially fatal hemolytic transfusion reaction.
So the only blood a Bombay individual can safely receive is
Blood from another Bombay individual.
But if they look identical to a normal Group O on a standard front type, how does a technologist actually catch a Bombay before it's too late? Like, we can't just guess.
No, we rely on a specific plant seed extract known as a lectin.
Lectins, right?
Yeah, lectins are these fascinating proteins that happen to bind to very specific carbohydrate determinants on red cells, basically mimicking the behavior of antibodies.
Okay, so which one do we use here?
To prove the definitive presence or absence of the H antigen, we use the lectin derived from the plant Ilex europaeus. This specific lectin acts as an anti-H reagent.
So if I take a drop of Ilex europaeus and add it to a tube of normal Group O cells, those cells will clump up.
Yes, they'll agglutinate because the O cells are covered in exposed H substance.
But if I drop it onto Bombay cells,
You'll see zero agglutination. The Bombay cells will completely ignore the Ilex europaeus, proving definitively that they lack the H substance.
and that single negative tube is what saves the patient's life.
It really is.
Okay, before we move off the molecular level, we need to address the subgroups. Because Group A is not just one monolithic flavor, right? We have A1 and A2.
The principal subgroups of A are a vital concept for the boards. The serological difference between them is based on their reactivity with another specific lectin.
Right, because most Group A individuals, roughly 80% of the population, are subgroup A1.
And the remaining 20% are A2 or even weaker, rarer subgroups like A3 or ECAS.
My understanding is that A2 cells contain physically less A antigen on their surface and proportionally more exposed H antigen than A1 cells.
That's correct.
So if we need to differentiate them in a clinical setting, what is our diagnostic tool?
We reach for a different plant lectin, Dolichos biflorus.
Galich's biflorus.
Yeah. It acts specifically as an anti-A1 reagent.
Yeah.
If you test a patient's red cells with it and they agglutinate strongly, the patient is an A1.
And if the cells do not agglutinate, they are an A2.
Exactly.
Okay, let's lock this in for you with an exam-style question. Imagine you're sitting for the boards.
Good idea.
The prompt states, your patient forward types as a group A. However, you notice they have an unexpected antibody in their reverse grouping that is reacting positively with your A1 reagent cells.
Okay.
What region are you reaching for to figure out what is going on?
You must reach for deletions by Forest. Because the patient is typing as an A, but their plasma is attacking A1 cells, you suspect they might be an A2 subgroup who has formed a naturally occurring anti-A1 antibody.
So testing their red cells with Dolichos biflorus will confirm they are indeed A2.
Which perfectly explains that unexpected reaction in their reverse type.
Nice. Let's quickly review the standard interpretation tables before we dive into how they fall apart. We have the forward grouping and the reverse grouping.
Forward grouping, which is also called cell grouping, is testing the patient's unknown red cells against known commercial reagent antisera at room temperature.
Right, we use reagent anti-A and reagent anti-B.
And the logic is purely physical. If the unknown cells mixed with the antisera result in no agglutination, it means the cells lack that specific antigen. If they agglutinate, the cells possess that antigen.
Simple enough. If they react with anti-A but not anti-B, they're group A. React with B but not A, they're group B.
Exactly.
Reacting with both makes them AB, and reacting with neither makes them group O. That is the front type.
Now consider the reverse grouping, or serum grouping. Here, we are testing the patient's unknown serum against known saline-suspended group A1 and group B reagent red cells, also at room temperature.
So we're hunting for the naturally occurring antibodies floating in the patient's plasma.
Precisely.
If their serum reacts with the B cells but ignores the A1 cells, they have anti-B in their plasma. And the only people who naturally have anti-B are group A individuals.
Right. If they react with the A1 cells but not B cells, they possess anti-A, making them group B.
If neither tube reacts, they lack both antibodies, meaning they're AB.
And if both tubes react violently, they possess both anti-A and anti-B, which confirms they are group O.
Okay, so in a perfect textbook world, the forward type and the reverse type will perfectly mirror each other.
They should inversely match.
But if the rules of the ABO system are so absolute, why do technologists spend half their shifts trying to figure out why the front and back types don't match?
Because human biology is messy.
It really is. This leads us into the territory the board exam absolutely loves, ABO discrepancies.
Yes, a massive topic.
What is the operational protocol when the tubes are essentially lying to us?
The very first action you must take when faced with an ABO discrepancy is categorization. You can't just start throwing reagents at the problem.
Right.
You must systematically divide the discrepancy into one of two distinct categories. Is this a problem originating with the red cells, meaning the forward type is giving us anomalous results?
Or is this a problem originating with the serum, meaning the reverse type is behaving strangely?
Exactly.
Let's investigate the red cell side first. What physical mechanisms cause extra or missing reactions on the front type?
Well, a remarkably common issue is rouleau, which fundamentally represents a failure to wash the patient's red cells adequately before testing.
We'll break down the specific physics of rouleau in a moment. What else?
You might also encounter a mixture of cell types. Consider a Group A patient who was bleeding out in the trauma bay and was emergency transfused with 6 units of uncross-matched Group O red cells.
Oh, wow. So when you draw their blood an hour later, you aren't just testing their blood, you're testing a cocktail.
Precisely. You'll observe a mixed field reaction under the microscope.
Mixed field?
Yeah, some of the patient's native A cells will be agglutinating into clumps, while the transfused O cells will be floating completely free in the background. It creates a very confusing macroscopic picture.
We also touched on subgroups earlier. An A2 patient might exhibit a significantly weaker than expected reaction in the front type compared to a standard A1.
Right, causing the technologist to question if it's a true positive.
And then you have the unusual genotypes, like our Bombay phenotype, which completely masks the patient's true genetic inheritance.
Furthermore, certain severe disease processes can actually alter the physical structure of the red cell.
Wait, really?
Yes. Specific leukemias can weaken the expression of A or B antigens on the red cell membrane to such an extreme degree that a Group A patient might temporarily forward type as a Group O.
That's wild. But I want to push on one of the strangest things in the source material, the acquired B phenomenon.
Ah, acquired B.
The chart mentions this happens with gut infections. How does an infection change a blood type?
It is a brilliant example of bacterial interference. Acquired B usually occurs in Group A patients suffering from severe bacterial infections of the gastrointestinal tract, like colon cancer or sepsis.
Okay.
Certain bacteria release an enzyme called a deacetylase into the bloodstream.
And what does that do?
This bacterial enzyme physically travels to the red blood cells and cleaves an acetyl group off of the patient's normal Group A immunodominant sugar.
It physically alters the molecular structure of the antigen while it's still attached to the patient.
It does. By removing that acetyl group, the bacterial enzyme transforms the Group A sugar so that its molecular shape looks incredibly similar to a Group B sugar.
Wow.
It's so similar that our commercial anti-B reagents are fooled into binding with it, causing a false positive reaction. The bacteria literally carved the sugar to fool a diagnostic test.
That is just wild. Okay, let's pivot to the other side of the discrepancy chart. Problems in the serum, the reverse type. What causes the plasma to betray us?
Here, we also encounter rouleau, but the manifestation is different. In the serum, rouleau is driven by pathologically increased serum proteins.
Like what?
We see this heavily in patients suffering from multiple myeloma or Waldenstrom's macroglobulinemia.
But how does excess protein cause cells to stick together if there's no antibody involved?
It comes down to the electrical charge of the red cell environment.
Okay, the zeta potential stuff.
Right. Normal red cells have a net negative surface charge, which causes them to naturally repel each other in suspension.
Makes sense.
But when a patient has massive amounts of heavy, positively charged proteins floating in their plasma, like the monoclonal immunoglobulins in multiple myeloma, those proteins alter the dielectric constant of the fluid.
So they essentially neutralize the repelling force between the red cells.
Exactly. Without that repulsion, the red cells naturally settle and stick together in long columns that look exactly like a stack of coins.
The stack of coins.
Yes, it completely mimics true agglutination, but it is entirely non-immune.
What about missing reactions in the back type? Who might be missing their expected naturally occurring isoagglutinins?
We typically look at the extremes of age.
Newborns and the elderly.
Correct. Newborns have immature immune systems. Their bodies haven't had sufficient time to build up their own ABO antibodies yet, so their reverse type is often completely blank.
And on the other end of the spectrum,
elderly patients frequently experience immune senescence, a natural, age-related decrease in overall antibody production, leading to very weak or totally absent reverse reactions.
You also have to consider patients with actively compromised immune systems. Right?
Yes, such as those with hypogammaglobulinemia or those undergoing heavy immunosuppressive chemotherapy. They simply lack the physiological machinery to produce enough antibodies to trigger a visible reaction in the tube.
Right.
Finally, you must account for unexpected cold-reacting antibodies in the serum.
Oh, this is a tricky one.
It is. Suppose a patient has a naturally occurring anti-M antibody. If the region A1 or B cells you are using for the reverse type happen to possess the M antigen on their surface, the patient's anti-M will attack those region cells.
And it'll cause a massive clump, giving you a false positive that has absolutely nothing to do with their ABO status.
Exactly.
Okay, so we know the traps. Now, how do we escape them? The boards want to know your exact resolution steps.
They definitely do.
Let's tackle rouleau first. I'm looking at the discrepancy resolution chart, and I have a question about the protocol.
Okay.
If rouleau affects both the red cells, causing front-type problems, and the serum causing back-type problems, why do we treat the resolutions entirely differently?
What do you mean?
Well, the chart states that for red cell problems, you resolve by repeating with saline-washed cells. But for serum problems, you must use a saline replacement technique. Why the discrepancy in resolving the discrepancy?
That is a phenomenal question, and understanding the physical difference between those two techniques is absolutely critical.
Let's hear it.
Let's look at the forward type first. You're trying to test the patient's physical red cells against commercial antibodies. The interference is caused by the patient's heavy, sticky plasma proteins coating those red cells.
Okay.
So the solution is purely mechanical. You take the patient's red cells, add normal saline, spin them down in a centrifuge, and pour off the liquid. You repeat this a few times.
You're physically rinsing the problematic plasma down the drain.
Yes. Now you have perfectly clean red cells to test against your region.
That makes perfect sense. You rinse the dirt off the car before you inspect the paint.
Exactly. But apply that logic to the reverse type. In the reverse type, you are testing the patient's serum to hunt for their specific antibodies.
Oh.
If you try to wash the patient's serum, you are washing away the very antibodies you're trying to detect. You cannot wash the test medium.
You are trapped. You have to let the reaction happen with all that sticky protein present.
You do. You mix the patient's thick serum with the reagent red cells, allow them to incubate, and spin the tube down.
And then what?
You have a clump at the bottom, but you don't know if it's a true antibody or antigen lattice or just a non-immune stack of coins. This is where the saline replacement technique comes in.
Okay.
You carefully pipette off the patient's serum from the top of the tube, leaving the red cell button completely undisturbed at the bottom. Then you replace that serum with pure neutral saline.
And what happens to the cells when you mix them back up?
Well, if the clump was caused by true agglutination, the strong chemical antibody-antigen bonds will remain perfectly intact. The cells will stay tightly clumped.
But if it was rouleau?
If the clump was merely rouleau, the neutral saline instantly disperses that high-protein environment. The electrical repulsion returns, and the stack of coins completely falls apart.
The rouleau dissociates.
Yes. It is an incredibly elegant physical way to differentiate a false, sticky phenomenon from a true immune reaction.
That is genuinely clever engineering. What about resolving the missing antibodies in our elderly patients or isolating those unexpected cold antibodies that are muddying the reverse type?
For those scenarios, we utilize a mini cold panel.
A mini cold panel.
The physical principle driving this technique is temperature thermodynamics. Lower temperatures inherently enhance the binding affinity of cold-reacting IgM antibodies, which includes our normal ABO isoagglutinins.
So if an elderly patient's anti-BP is just too weak to form a visible lattice at room temperature,
incubating the test tube at 4 degrees Celsius in the refrigerator might slow the molecular movement down just enough to give that weak antibody the thermodynamic boost it needs to bind and become visible, instantly resolving your discrepancy.
And the mini cold panel also helps with the opposite problem, unexpected cold antibodies causing false positives.
Yes. The mini cold panel involves taking the patient's serum and testing it against a specific array of cells, screening A and B cells, group O adult cells, group O cord cells, and an autocontrol where the patient's serum is tested against their own red cells.
So by looking at the pattern of reactions across those specific cells, you can deduce the culprit.
Exactly. If the serum reacts strongly with the adult O cells, but completely ignores the O cord cells, with near certainty you're dealing with an antibody.
And we'll explore exactly why cord cells lack that antigen shortly.
It's a rapid diagnostic triage to strip away the interference and reveal the true ABO type.
Love it. Once the ABO system is resolved and clear, we immediately have to confront the next most clinically significant threat in the blood bank. Let's examine the RH system.
The RH system is notoriously dangerous. The primary reason is that the D antigen is the single most immunogenic of all the blood group antigens we study.
Immunogenic meaning it's highly likely to provoke an immune response if introduced to someone who lacks it.
Highly likely. If a completely D-negative individual is exposed to a single unit of D-positive blood, they have an extraordinarily high probability of permanently forming an anti-D antibody.
This makes routine D-grouping testing for the presence or absence of the D antigen using an anti-D reagent absolutely vital.
Without a doubt.
But just like ABO, the RH system refuses to be binary. We have to discuss the weak D phenotype.
Weak D is a scenario where the patient physically possesses the D antigen on their red cell membrane. But for a variety of genetic or structural reasons, perhaps the antigen is buried deep in the membrane or they inherited a mutated allele, it's expressed so weakly that a standard room temperature test with anti-D might appear completely negative.
The antigen is there, but it's hiding from our standard reagents. So how do we force it out of hiding?
We push the thermodynamics. We take the negative tube, incubate it at 37 degrees Celsius to mimic core body temperature and promote optimal IgG binding. And we wash the cells and carry the test through the anti-human globulin or AHG phase.
Okay, and if it reacts then?
If the cells agglutinate only after adding AHG, they are classified as weak D positive. Clinically, they are considered D positive.
This brings up a massive point for the exam regarding clinical protocols. I know for a fact that hospitals do not perform a 37-degree AHG weak D test on every single patient who types as Rh negative. It would take way too much time.
Way too much time.
So who actually requires this extended testing?
Testing for weak D is strictly required for two specific populations: blood donors and obstetrics patients.
Let's think about the logic. For blood donors, we absolutely must know if they have even a microscopic trace of D antigen on their cells.
Right, because if we mistakenly label a weak D donor as Rh negative, and we transfuse that unit into a truly Rh negative recipient, that hidden D antigen will stimulate the recipient's immune system to form anti-D.
So a weak D donor is treated as D positive to protect the blood supply. What about the OB patients?
For pregnant women, we need to know their exact, definitive D status to determine if they are candidates for Rh immune globulin, commonly known as RHIG.
Right.
If a mother is truly D negative, she needs RHIG to prevent her from forming anti-D if her baby happens to be D positive, which would cause hemolytic disease of the newborn in future pregnancies.
And if she's weak D positive?
She already has the D antigen, so she doesn't need the RHIG.
Let's talk about the reagents we use to hunt for this antigen. The source chart spends a lot of time comparing monoclonal anti-D to high-protein anti-D. Why does the protein concentration of the reagent matter so much?
It's really a matter of historical engineering. Historically, anti-D reagents were derived from human plasma and were exclusively IgG antibodies.
And Ig antibodies are physically very small, right?
Yes, they have a hard time bridging the gap between two mutually repelling red cells to cause visible agglutination.
So to force the agglutination.
Manufacturers added massive amounts of albumin and other proteins to the region. These high-protein media reduce the repelling forces, allowing the small IgG antibodies to cross-link the cells.
But there is a massive downside to adding all that sticky protein, isn't there?
A huge downside. Those high-protein reagents were incredibly sticky. They frequently cause false positive spontaneous agglutination. The red cells would just clump up because of the thick protein syrup, mimicking a positive reaction. To combat this, whenever a technologist used a high-protein anti-D reagent, they were absolutely mandated to run a D-control tube in parallel.
Walk us through the physical setup of that D-control.
The D-control tube contained the exact same heavy, sticky, high-protein media as the reagent tube, but it completely lacked the actual anti-D antibodies.
So you place the patient's cells in the reagent tube, and you place the patient's cells in the control tube.
Right.
If the D test is positive, but the D-control tube also clumps up, what does that tell the technologist?
It tells them their test is entirely invalid.
Invalid.
Yes. If the control tube is positive, it proves that the patient's cells are agglutinating simply because they're sitting in sticky protein, or perhaps because they're already coated with autoantibodies inside the patient's body. A positive direct antiglobulin test, or DAT.
So you cannot trust the positive result in the anti-D tube.
Because the cells are proving they'll clump up on their own, regardless of whether the anti-D antibody is present or not. The D control must be completely negative for the D grouping to be valid.
Thankfully, modern technology has largely saved us from that sticky syrup. Most labs today use monoclonal or chemically modified anti-D reagents.
Correct. Modern bioengineering allows us to use low-protein anti-D reagents that have a protein content comparable to our standard ABO reagents.
Nice.
Because they are not inherently sticky, a separate D control tube is usually entirely unnecessary. The negative reactions you observe in the anti-A or anti-B tubes serve as a built-in control, proving that the patient's cells aren't just spontaneously agglutinating in low-protein environments.
But the board exam loves exceptions. There is one specific scenario where even with modern low-protein reagents, you are absolutely required to run a control.
Oh, yes. And that scenario is when a patient types as AB positive.
Think about the physical tubes in your rack.
The patient agglutinated in the anti-A tube. They agglutinated in the anti-B tube. And they agglutinated in the anti-D tube.
Every single tube is clumped.
Every single one. You do not have a single negative tube on your rack to prove that these cells aren't just spontaneously agglutinating everywhere due to some underlying pathology.
So in that specific scenario, to prove the AB positive result is real,
you must run a separate saline control, a 6 to 8% albumin control, or an auto control.
Excellent. Before we leave the RH system, we have to touch on the genetic extremes, the unusual phenotypes like RH null and deleted cells.
RH null is a fascinating and medically severe condition. These individuals inherit genes that result in a complete absence of every single Rh system antigen. No D, no C, no E, no C, no E.
Wow.
But you have to understand that these antigens aren't just decorative flags on the cell surface. The Rh structural proteins are integral, physical, load-bearing pillars of the red blood cell membrane itself.
So if you remove all the load-bearing pillars, the structure collapses.
Precisely. Without those Rh proteins, the cell membrane is physically compromised. It is structurally weak.
So what happens to the patient?
These patients suffer from a chronic, lifelong hemolytic anemia simply because their red cells are incredibly fragile and shatter easily as they navigate the spleen and capillaries.
What about deleted cells? The chart notes them as -D-.
Deleted cells simply mean the patient is missing one or more of the normal Rh alleles. most commonly the entire C&E series.
So their red cells express only the D antigen.
Right, but often in massively elevated quantities because there are no other Rh antigens competing for real estate on the membrane.
Okay, so if the ABO system and the Rh system are the main characters of the blood bank, the other blood group systems are the character actors that cause all the plot twists.
The alphabet soup. There are dozens of them. And for the exam, trying to memorize them as a single list is a recipe for failure.
So how do we handle them?
You have to divide and conquer them based on their physical behavior. The most effective way to do this is to divide them into two distinct camps: the cold-reacting IgM antibodies and the warm-reacting IgG antibodies.
Let's start out in the cold. The IgM cold reactors. I know there's a memory device from the study guide involving an igloo and Louis the Eskimo to help remember these.
Yes, that's a great one.
The cold reactors generally include Lewis I, P, M, and N. Let's unpack Lewis first.
The Lewis system is entirely unique in its physical mechanics. Lewis antigens are not actually produced by the red blood cell itself.
Wait, really?
Yeah, they are not anchored into the membrane during cell development. They are plasma antigens, specifically glycosphingolipids, that are produced by various tissue cells and secreted directly into the plasma.
Okay.
As the red blood cells circulate through the body, they literally absorb the Lewis antigens directly out of the plasma onto their surface.
They act like little sponges, just picking up the antigens as they float by in the bloodstream.
That is exactly the mechanism. And because they must be absorbed from the plasma after the cell is circulating, Lewis antigens are physically not present on newborn cord cells.
A newborn's red cells haven't had time to soak them up yet.
Therefore, newborns almost universally type as Lin, A negative, B negative.
The source material also highlights a bizarre phenomenon regarding pregnant women and their Lewis antigens.
Yes, during pregnancy, women's red cells frequently and temporarily lose their Lewis antigens.
Lose them.
Yeah, the exact mechanism involves changes in plasma lipoproteins during gestation, but the result is that pregnant women may transiently type as LA negative, B negative.
Wow.
Because they temporarily lose the antigen, their immune system might temporarily recognize Lewis as foreign, and they can form transient Lewis antibodies during their pregnancy.
But do these maternal Lewis antibodies pose a threat to the baby? Are we worried about hemolytic disease of the newborn?
We are not worried at all for two highly physical reasons. First, Lewis antibodies are almost entirely IgM-class immunoglobulins.
And IgM molecules are huge.
They're massive pentamers that are physically too large to cross the placental barrier. They cannot reach the baby.
And the second reason.
Second, even if they could cross the placenta by some miracle, we just established that fetal red cells haven't absorbed Lewis antigens yet. There is no physical target on the baby's cells for the antibody to attack.
Therefore, Lewis definitively does not cause HDN.
Exactly.
That is a perfect example of knowing the why. Okay, the next resident of our cold igloo is the I and I system.
The I system is a beautiful demonstration of developmental biology. The big I and little I are not separate genetic alleles fighting for dominance. They represent developmental stages of the exact same carbohydrate chain on the red cell.
Oh, interesting.
Infants are born with simple, linear carbohydrate chains extending from their cells. This linear structure expresses the little I antigen.
So cord blood cells are strongly little I positive and big I negative.
Yes.
But babies don't stay babies. As the infant matures over the first 18 months of life, what happens to those linear chains?
They branch out. Biological enzymes add complex branches to those simple linear chains. The physical act of branching creates the structural epitope we recognize as the big I antigen.
So as you become an adult, your little I antigens are converted into big I antigens.
Almost all adults are big I positive and little I negative.
So consider the clinical implication. If an adult patient forms an auto-antibody, which is a common cold-reacting IgM, that antibody is going to react with almost every single adult red cell on your testing panel.
Because almost all adult cells have that branched big I antigen.
It creates a massive headache for the technologist.
It causes panagglutination at room temperature,
Right.
which completely masks any other far more dangerous IgG antibodies that might be hiding underneath.
So to strip away that interference,
We often utilize the pre-warm technique, maintaining all reagents and saline strictly at 37 degrees to physically prevent that cold IgM from binding, allowing us to see what is underneath.
next step in the cold system is the P system. What is the crucial physiological takeaway here?
There are two main concepts to lock in. First, the physical P1 antigen naturally deteriorates very quickly upon storage in a refrigerator.
Okay, so if you are testing a unit of donor blood or a bottle of screening cells that is nearing its expiration date, a weak P1 antigen might have completely degraded, leading to false negative phenotyping.
Right. The second, much more heavily tested concept is the specific antibody anti-P.
The infamous Doneth-Landsteiner antibody. This is a huge board topic.
It absolutely is. Anti-P is a powerful autoantibody frequently found in a severe clinical condition called paroxysmal cold hemoglobinuria, or PCH.
PCH.
The defining characteristic of the Doneth-Landsteiner antibody is that it is a biphasic hemolysin.
Biphasic, meaning it requires two distinct temperature phases to execute its damage. How does it physically work inside a patient?
Imagine a patient with PCH walking outside on a freezing winter day. In the colder peripheral extremities of their body, their fingers, their toes, the tip of their nose, the blood temperature drops.
Okay.
In this cold phase, the anti-P antibody binds tightly to the red blood cells, but it doesn't destroy them yet.
So it just waits.
Then, as the patient goes back inside and that chilled blood circulates back into the warmer 37-degree core of their torso, the temperature shift triggers the second phase.
And what happens?
The bound antibody violently activates the complement cascade, causing massive, devastating intravascular hemolysis.
It sets the explosive charge in the cold, and it detonates the charge in the warm. Biphasic. That is an incredible mechanism.
It's a perfect encapsulation of why temperature control in immunohematology is not just a laboratory guideline, it's a reflection of human physiology.
Let's look at the last major residence of the cold IgM category, the MNS's system.
M and N are codominant alleles. The antibodies against them, anti-M and anti-N, are primarily cold-reacting IgMs, though there are rare IgG variants of anti-M that can cross the placenta.
But the absolute highest yield board fact regarding the M and N antigens is their propensity to exhibit something called dosage.
Dosage, a concept that haunts MLS students.
It really does. Let's break down the physical reality of dosage on the cell membrane.
The red blood cell membrane only has a finite amount of physical surface area, a limited number of anchoring sites for these specific proteins.
Right.
Dosage means that an antibody will react much more aggressively with a red cell that has a homozygous genetic expression of the antigen compared to a heterozygous expression.
Let's visualize the genetics. If a red cell inherited the M gene from both its mother and its father, it's homozygous. Its genotype is M. That cell dedicates 100% of those specific membrane anchoring sites to building M antigens. It has a massive double dose of M on its surface.
And if you test that homozygous MM cell with an anti-M antibody, the reaction will be violently strong, a solid 4+ clump, because there's a massive density of targets.
But what if this cell is heterozygous? What if it inherited an M from dad, but an N from mom? Its genotype is MN.
Now the red cell has to share that limited surface area. Half the sites are building M antigens and the other half are building N antigens. The cell only has a single dose of M.
Because the physical density of the M antigen is cut in half, the anti-M antibody has a much harder time finding targets to cross-link.
Exactly. The agglutination will be significantly weaker, maybe only a 1+ or 2+ reaction. Sometimes it's so weak it doesn't react at all. That is dosage.
The strength of the test tube reaction changes based on the genetic dose of the antigen.
You got it.
The other critical exam fact for the MNS system involves their physical interaction with our laboratory enhancement media. Specifically, the study guide highlights a mnemonic involving enzymes. Kivifacin, the lumberjack. What does the lumberjack do to M and N?
The lumberjack chops them down.
Chops them down.
The M and N antigens are physically located on the outer edge of a glycoprotein called glycophorin A. They're very exposed.
Okay.
If you treat those red cells with routine blood bank proteolytic enzymes like ficin, papain, or bromelain, those enzymes act like chemical machetes. They literally cleave the glycoprotein, completely chopping off the M and N antigens.
So if you test enzyme-treated cells with anti-M or anti-N, you will get a completely negative reaction because the targets have been destroyed.
Exactly.
Okay, we're officially moving out of the cold. Let's explore the IgG warm reactors. The study guide uses the jungle gene story to remember these, encompassing the RH system, Kell, Kidd, and Duffy.
These are the antibodies that truly terrify technologists because they are the primary culprits behind severe delayed hemolytic transfusion reactions and hemolytic disease of the newborn.
So let's analyze Kell first.
The Kell system demands immense respect in the laboratory. The K antigen big K is the second most highly immunogenic antigen in human biology, right behind the RHD antigen. It provokes a fierce immune response.
But the statistical reality of Cal offers a silver lining, doesn't it?
It does. While it is highly immunogenic, the big K antigen is relatively rare. Approximately 91% of the human population is natively Cal negative.
So if your patient unfortunately forms a strong anti-K antibody, finding compatible blood for them is actually a relatively stress-free endeavor.
Statistically, 9 out of 10 random donor units you pull from your refrigerator will naturally lack the big K antigen and be perfectly compatible.
Now let's contrast that with the system that offers zero silver linings, the KID system,
Yeah.
JCA and JKB. Listeners put a massive asterisk next to this. The board exam is obsessed with KID.
KID antibodies are infamous. They are the quintessential classic cause of severe, life-threatening delayed hemolytic transfusion reactions.
And the danger lies entirely in the specific physiological behavior of their antibody titer.
Yes.
Explain the titer behavior. Why is it so stealthy?
Suppose a patient is transfused with JICA-positive blood, and they form an anti-JICA antibody. Their immune system logs the threat.
Right.
But over time, sometimes just a few months or years, the titer, which is the physical concentration of that antibody circulating in their plasma, begins to plummet. It drops so low that it frequently falls below the detection threshold of our most sensitive laboratory equipment.
So 10 years later, that patient comes into the emergency room needing blood. We draw their blood, we run a comprehensive antibody screen, and the test tube is stone cold negative. We see nothing.
We see nothing, so we assume they have no antibodies. We cross-match a unit of JICA-positive blood. It looks perfectly compatible in the test tube, so we hang the bag and transfuse the patient.
This is where the disaster strikes.
The patient's immune system, which still harbors the memory B cells for that specific antigen, detects the massive influx of JICA donor cells.
Oh, boy.
It triggers an anamnestic response, a rapid, violently explosive secondary immune reaction. Within a matter of days, the patient's antibody titer skyrockets, and their body aggressively destroys every single transfused red cell.
It's the ultimate stealth attack. Serologically, how do KID antibodies behave when we can actually see them?
They are warm-reacting Igs. They frequently exhibit dosage, just like M and N, but their defining laboratory characteristic and a crucial exam differentiator is their reaction to enzymes.
Let's use an analogy here to contrast KID with Duffy and MNSs, which we just said get destroyed by enzymes.
Yeah.
I like to visualize these antigens wearing different types of clothing.
Okay, I like it.
The M, N, and Duffy antigens are wearing highly fragile, delicate knit sweaters. If you treat them with a proteolytic enzyme or lumberjack, the enzyme easily chews up the fragile sweater, the antigen is destroyed, and the reaction disappears.
That is a highly effective visualization.
Yeah. But the KID antigens, JICA and JKB, are not wearing fragile sweaters. They are wearing solid steel plate armor.
Exactly.
They're anchored tightly and close to the red cell membrane. When you unleash the proteolytic enzymes on a KID antigen, the enzyme cannot destroy the steel armor.
Instead, the enzyme runs around chewing off all the surrounding sialic acid and bulky proteins that were getting in the way.
The enzyme essentially polishes the armor. By clearing the brush, the enzyme allows the KID antibodies to bind even tighter, making the agglutination reaction significantly stronger.
There's precisely the mechanical reality. Enzymes destroy Duffy, M, and N, but they powerfully enhance KID and RH reactions.
Let's dive deeper into the Duffy system, PHIA, and Fib, because the source material ties it directly to evolutionary biology.
Duffy is one of the most remarkable intersections of immunohematology and global epidemiology.
How so?
The Duffy glycoproteins in the red cell membrane serve a physiological purpose beyond just being blood-type antigens. They are the specific entry receptors utilized by Plasmodium vivax, a parasite responsible for a major form of malaria.
The parasite literally latches onto the Duffy antigen to pull itself inside the red blood cell and cause infection.
Exactly.
So, logically, if a human being's red cells completely lack those Duffy receptors, the parasite is locked out. It cannot enter the cell.
It is completely locked out. Over thousands of years, through intense natural selection in geographic regions where Plasmodium vivax malaria was highly endemic, primarily in West Africa, a genetic mutation that silenced the Duffy genes became a massive survival advantage.
Those individuals survived malaria and passed on their genes.
Today, because of that evolutionary history, approximately 68% of the African American population exhibits the Phi a negative B negative phenotype,
They completely lack both antigens.
granting them innate, natural resistance to that specific strain of malaria. It is a textbook example of human genetics adapting to a lethal environmental pathogen.
I love how these microscopic sugars tell the story of human evolution. To recap our warm antibody section with a classic board question.
Okay, lay it on me.
If your patient has a documented historical record of a clinically significant antibody, but their current stat antibody screen at admission is completely negative, which stealthy blood group system are you immediately worried about?
You are immediately terrified of the kid system JKK, or JKB, due to that notorious rapid drop in antibody titer and the subsequent risk of a massive anamnestic delayed transfusion reaction.
Awesome. Let's transition into the legal side of the laboratory. We have spent an hour dissecting how these antigens behave.
Yes, their clinical behavior.
Because these antigens are inherited in strict, predictable Mendelian patterns from parent to child, they serve as literal genetic fingerprints. Let's examine how the board exam tests your knowledge of inheritance through serologic parentage testing.
Well, it's absolutely true that modern real-world paternity cases rely almost exclusively on high-resolution molecular DNA sequencing. The ASCP board exam still requires you to master the logical puzzles of serological inheritance rules.
When we're looking at parentage, the most fundamental baseline rule is maternity is always assumed to be true.
The entire purpose of the testing is to determine if the alleged father can be mathematically excluded from possibility.
And there are two distinct categories of exclusion: direct exclusion and indirect exclusion. Let's define the mechanics of a direct exclusion first.
A direct exclusion is the strongest evidence you can have serologically. It occurs when a specific genetic marker is physically present on the child's red cells, but is completely absent from both the mother and the alleged father.
Let's run a hypothetical based on the source charts.
Sure.
Imagine the alleged father tests negative for the KEL antigen. He is big K negative. The mother also tests negative for the KEL antigen. She is big K negative. However, when we test the baby's cord blood, the baby types as strongly big K positive.
That scenario results in a direct exclusion of the alleged father.
Because neither he nor the mother possess the big K gene in their DNA to pass down.
The baby had to inherit that dominant big K gene from a different biological source. That is a direct, irrefutable, hard exclusion based on the presence of a foreign antigen.
Okay, what constitutes an indirect exclusion? The logic here feels a bit more fragile.
It is. An indirect exclusion is based on assuming a parent's genotype based on their serological phenotype. It happens when the child lacks a genetic marker that the alleged father must have transmitted if our assumptions about his genotype are correct.
Let's walk step by step through the specific visual data set provided in the source material to see how this plays out.
All right, let's do it.
The exam prompt asks, is the alleged father, based on the testing below, excluded? Here's the data we receive. The alleged father's blood tests positive with anti-K and completely negative with anti-little k.
So looking at his tubes, he appears to be homozygous big K, big K.
The mother's blood tests negative with anti-K and positive with anti-K. She cures homozygous little k, little k.
And the baby?
The baby tests positive for both. The baby is heterozygous big K, little k. Does this data exclude the father?
To solve it, you track the obligatory genes. The mother is little k, little k. She is biologically obligated to pass a little k to the child.
We look at the baby. The baby has a little k. The maternal contribution matches perfectly.
Now look at the alleged father. Because he only reacted with the big K and Ticera, we assume his genotype is homozygous the big K. Big K. Therefore, he must pass a big K to every single child he ever fathers.
We look at the baby. Does the baby possess a big K? Yes, the baby is K.
The alleged father successfully passed his obligatory genetic marker to the child. Therefore, there is no exclusion. His genetic contribution perfectly matches the child's physical phenotype.
But I want to push back on the fundamental premise of the indirect exclusion because it seems to have a massive logical loophole.
Oh, it absolutely does.
An indirect exclusion relies entirely on us assuming a person is homozygous just because their red cells only reacted with one specific anti-sera. But what if there is a silent allele?
Let's explore that. What do you mean?
Suppose we have a different alleged father. We test him, and he types as big K positive and little k negative. The serologist assumes he is homozygous KK, meaning he must pass a big K. But what if his actual hidden genotype is K0? What if he possesses one big K gene and one silent recessive amorph gene that produces no antigen at all?
Hmm.
If he passes that invisible silent zero gene to the child will lack the big K that the court thought the father was obligated to transmit. Does a single indirect exclusion actually hold up as proof in a court of law?
You have just perfectly articulated the exact vulnerability of red blood cell serologic testing and why it's designated as merely indirect.
Because of the constant looming possibility of silent alleles, null phenotypes, or genetic microdeletions that serology simply cannot visualize on a test tube level.
Exactly. A single indirect exclusion is virtually never considered sufficient evidence to definitively rule out paternity in a legal setting. It creates statistical doubt, but it is not biological proof.
And that is exactly why molecular DNA analysis has completely usurped red cell serology.
DNA testing looks directly at the sequence of the nucleotide base pairs, completely eliminating the guesswork and the blind spots of silent alleles.
Okay, we have arrived at the final practical phase of our deep dive. We have memorized the molecular structures of the antigens. We know their clinical quirks and how they behave in the cold versus the warm.
But how do we actually force them to reveal themselves in the laboratory?
We must master the physical steps of the indirect antiglobulin test, the IAT, and the specific chemical enhancement media we use to accelerate the reactions.
The IAT is the absolute bread and butter protocol of the blood bank. It is the antibody screen.
But human IgG antibodies are slow to bind in a simple saline suspension.
To make the test efficient enough for a fast-paced hospital, we rely on enhancement media to manipulate the thermodynamic and electrical environment of the test tube to force the antibodies onto the antigens faster. The study guide provides an excellent comparison of our chemical toolkit.
Let's break down the physical mechanisms of each tool. First on the list, low ionic strength saline, or LISS. How does it physically speed things up?
LSS functions by aggressively manipulating the electrical charge surrounding the red blood cells. Normal red cells in suspension are surrounded by a cloud of positively charged ions that are attracted to the cell's negative surface.
This creates an electrical force field called the zeta potential, which keeps the cells separated.
LSS literally decreases the ionic strength of the fluid medium. By reducing the number of ions in the fluid, it drastically lowers the zeta potential.
With that electrical force field reduced, the positively charged IgG antibodies can physically approach the red cells much faster and with much less resistance.
The ultimate advantage of LASS is speed. It significantly increases the rate of antibody uptake, allowing us to safely shorten our required incubation times from an hour down to just 10 or 15 minutes.
Next on the chart, enzymes. We already talked about bromelain, pacin, and papain acting like lumberjacks on the Duffy and M&S's antigens, but how do they actually draw cells together?
Beyond just destroying certain fragile proteins, enzymes literally act as chemical scissors, cleaving thousands of molecules of sialic acid completely off the surface of the red blood cell membrane.
And sialic acid is highly electronegative. It's the primary molecule responsible for the cell's net negative surface charge.
By shaving off the sialic acid, the enzyme drastically reduces the overall negative charge, which in turn violently reduces the repelling forces between the cells, allowing them to physically drift much closer together.
This proximity heavily promotes cross-linking and agglutination for the antibodies that survive the enzyme treatment, like Rh and KID.
Let's look at polybrine next.
What's its mechanism of action?
Polybrine is a massive, positively charged macromolecule. When you drop it into a test tube, it binds to the negative red cells and neutralizes their charge so completely that it causes severe, nonspecific, spontaneous aggregation.
It violently forces all the red cells to clump together into a massive ball, regardless of whether an antibody is present or not. That sounds like it would ruin the test.
How do you tell if there is a real antibody in there?
Yeah, how?
By using a neutralizing agent. You force the cells together with polybrine, so that any weak antibodies present are guaranteed to be within physical reach of an antigen to form a crosslink. Then, you add a citrate solution to neutralize the polybrine. If there was no real antibody present, the nonspecific aggregation simply reverses and the cells drift apart. But if a true IgG antibody took advantage of that forced proximity to build a chemical lattice, that specific agglutination will endure the neutralization and the clump will remain visible.
That is a brutally effective technique. Finally, we have PEG, or polyethylene glycol.
PEG is a fascinating water-soluble polymer. It does not alter the charge of the red cells at all. Instead, it alters the spatial environment.
How so?
PEG macromolecules are huge, and they physically take up a massive amount of space in the test tube, sterically excluding the water molecules.
By effectively sucking the water out of the test environment, PEG forces the remaining antibodies in the patient's serum into a much tighter, highly concentrated space directly surrounding the red cells.
By increasing the local concentration of the antibody, you massively promote its uptake onto the antigen. PEG is incredibly sensitive, making it the premier choice for hunting down very weak warm autoantibodies and low antibodies that might escape LASS.
But if PEG is so sensitive, why don't we just use it for everything? Why use LAS at all?
Because in laboratory medicine, hypersensitivity often comes at the cost of specificity. PEG is so incredibly efficient at forcing antibodies onto red cells that it will often force clinically insignificant weak warm autoantibodies to bind, creating a haze of false positive reactions that drive technologists crazy and delay patient care.
LASS strikes a better balance for routine screening.
Exactly.
So we've selected our enhancement media. Let's walk chronologically through the actual physical steps of the IAT procedure. We pipette the patient's unknown serum into a tube containing our known commercial screening cells, and we add our LASS or PEG. Step 1, incubation.
You place the rack of tubes into a heat block set precisely at 37 degrees Celsius. This simulates core body temperature.
During this 15-minute incubation phase, the IgG antibodies, if they're present in the patient's serum, will physically collide with and attach to their corresponding antigens on the region red cells.
After the timer goes off, you pull the tubes and inspect them specifically for hemolysis. Some highly aggressive antibodies can activate complement and cause the red cells to physically lyse and rupture right in the incubator. A pink or red supernatant is a definitive positive result.
Assuming there's no hemolysis and the fluid is clear, we move to the most critical physical manipulation of the entire protocol, the wash phase.
This is the moment where technologists must be utterly flawless in their technique. You place the tubes in an automated cell washer, which blasts the red cells with massive volumes of normal saline, spins them down into a tight button, and decants the liquid away.
You repeat this violent rinsing process 3 or 4 times. The physical goal is to completely and totally flush every single trace of unbound, free-floating serum protein and human immunoglobulin out of the test tube, leaving only the red cells and whatever antibodies are physically anchored to them.
Why is that flushing process so incredibly crucial? What is the catastrophic danger of sloppy, inadequate wash?
To understand the danger, you must look at the very next region you add. After the wash, you add anti-human globulin, or AHG.
Right.
AHG is an engineered animal antibody, usually from a rabbit, that is specifically designed to hunt down and bind to human IgG molecules.
The entire goal of the test is for the AHG to drop into the tube, find the human IgG antibodies that are attached to the red cells, grab onto them, and link the red cells together into a visible clump.
But what if you didn't wash well? What if there are still thousands of unbound human IgG antibodies just floating freely in the saline liquid?
Then disaster strikes. The moment you drop the AHG region into the tube, it immediately collides with and binds to all of those free-floating human antibodies in the liquid.
The AHG is completely neutralized.
It is entirely consumed and exhausted by the free-floating trash before it ever has a chance to reach the red blood cells at the bottom of the tube.
I love an analogy for this to make it stick. Washing the cells is functionally identical to rinsing shampoo out of your hair before you add a high-end conditioner.
Oh, that's a good one.
The unbound, free-floating proteins in the patient's serum are the shampoo. If you do not rinse them out of your hair completely, what happens when you add the conditioner? Your expensive AHG conditioner just clobs onto the leftover shampoo bubbles.
Right.
It interacts with the foam and never actually penetrates down to the hair follicle, the red blood cell itself. It is completely wasted.
That is a phenomenal conceptualization of AHG neutralization. And because a sloppy wash completely neutralizes the region, the red cells will not agglutinate. Your test tube will look perfectly smooth and negative.
But it's a lethal false negative. You just missed a potentially deadly KID or KEL antibody simply because you didn't rinse the shampoo out of the tube.
Because human error is inevitable, and a false negative can kill a patient, the blood bank protocol has a mandatory built-in safety net to catch this exact error.
The check cells, also known as Coombs control cells. How do they save us?
To every single test tube that appears negative at the end of the AHG phase, you are legally required to add 1 drop of Ig-sensitized check cells. These are commercial, laboratory-manufactured red cells that already have human IgG antibodies permanently and firmly attached to their surface.
So if my patient's tube looks negative, I drop in my check cells, I spin the tube one last time in the centrifuge, and what must I see when I look at the cell button?
You must see positive agglutination. Why? Because if you executed your wash phase perfectly, you flushed away all the free-floating proteins. That means the AHG reagent you added is still active, fully potent, and just sitting in the clear liquid waiting for a target.
You just handed it a massive target.
The check cells.
The active AHG instantly binds to the check cells, forcing them to clump.
Seeing that clump is your visual proof. Your check cells are the mirror telling you that you rinsed the shampoo out perfectly and your conditioner was working.
Precisely the opposite is also true. If you add your check cells, spin the tube, and they do not agglutinate, your test is completely invalid. It means the AHG reagent was either accidentally left out of the tube entirely or it was completely neutralized by a sloppy wash.
You cannot trust the initial negative result, and you must throw the tube away and start the entire procedure over from scratch.
There's one final specialized technique mentioned in the antibody hunting section, the pre-warmed technique. The chart lists this as a method to eliminate reactions due to cold antibodies. How do we physically execute a pre-warmed panel?
Imagine a patient whose plasma contains a violently strong, clinically insignificant cold autoantibody, like a massive anti-IA. If you perform a standard IAT, that cold antibody will aggressively bind to the red cells while the tubes are sitting on the benchtop at room temperature before you even put them in the incubator.
Once it binds, it's stuck there. It will carry all the way over to the AHG phase, cause a massive clump, and completely mask any real dangerous IgG alonobodies that might be hiding underneath.
To stop that from happening, we manipulate the environment to ensure the cold antibody never feels comfortable enough to bind.
Exactly. You utilize the pre-warm technique. You place the patient's unmixed serum into a test tube. You place your reagent red cells into a separate test tube. You put both isolated tubes into the 37-degree incubator and let them physically warm up to core body temperature before you ever allow them to catch.
You do not let them meet in the cold.
Never. Once they are hot, you mix them together inside the incubator. You let them incubate hot. And crucially, when it is time for the wash phase, you must wash them rapidly using saline that has been preheated in an incubator to 37 degrees.
By maintaining the physical environment strictly at body temperature from start to finish, you thermodynamically prevent the cold IgM antibody from ever attaching to the red cells, allowing you a clear, unobstructed window to see if any dangerous, warm-reacting IgG antibodies bind during the test.
It is a beautiful physical workaround to a chemical problem. Well, look at the time. We have navigated an absolutely massive amount of high-yield territory today. We started at the literal genetic building blocks, examining how glycosyltransferases build the A, B, and H sugars, and how the absence of that H foundation creates the lethal Bombay phenotype.
We waded through the frustrating, non-immune physics of Rouleau and Waldenström's and the bacterial deception of acquired B.
We analyzed the immune threat of the Rh system and the structural collapse of Rh null cells. We categorized the vast alphabet soup of the minor blood groups, detailing the biphasic explosive nature of the Donath-Landsteiner antibody, the stealthy anamnestic strikes of the KID system, and the evolutionary shield of the Duffy glycoproteins against malaria.
We navigated the logical traps of indirect paternity exclusions. And finally, we walked step by step through the thermodynamics of the IAT, the critical physics of the wash phase, and the life-saving validation of the check cells.
It's a staggering amount of technical information. But as you prepare for the boards, remember that the exam isn't designed to trick you. It's designed to ensure you understand the physical reality of the laboratory.
When you understand the physiological reasons why proteolytic enzymes polish the armor of the KID antigen, but destroy the fragile sweater of the Duffy antigen, or why an inadequate wash neutralizes your AHD, the memorization becomes entirely secondary.
You aren't just reciting a chart from a textbook, you understand the biological mechanics. That's the ultimate goal. I want to reassure you listening right now. The ASCP board exam is a formidable challenge, but you possess the foundational knowledge. You know the why behind the reactions now. Take a breath, trust your preparation, rely on the physics, and remember the mechanics.
I'll leave you with one final, broader thought to reflect on as you return to your studies. Every single time you sit down at the bench and perform an antibody screen, you're doing much more than just mixing clear liquids in a plastic test tube. You are literally reading a patient's evolutionary history, like the Duffy resistance to Plasmodium vivax.
You're reading their past environmental exposures, their prior pregnancies, their deepest genetic code. all of it is being translated and revealed right before your eyes through the incredible visible language of serology.
Exactly.
Those diagnostic muddy waters we talked about at the beginning are actually a crystal clear genetic fingerprint, provided you understand the physics of how to read the reaction. Good luck on the exam. You've got this.